Hello, everyone. My name is Shah Kabir, and my research partner, Dr. Sharma, and I will be offering this presentation. It's a really an exciting environment. And what this is all about harnessing geothermal energy by circulating fluid in a wellbore. So we'll explain that as we move along. So what's our motivation? Suffice it to say that given the climate change is upon us, we want to minimize the carbon footprints. That's one of the main drivers. And the question is, if we want to extract thermal energy by circulating fluid, where would we use them? Well, there are two options. One is to use for various industries, as we will see in the next slide. And the other item would be your power generation. So for power generation, we need fluid temperature at a high level, and the prospects may be limited, but we'll see where that takes us. So our focus would be what we can do in the US, but certainly we can take it elsewhere around the globe. So here is the British Petroleum's outlook, and there are similar outlooks published. So what we see that both the oil and the coal are on decline. That's the projection. Whereas the good news is the renewable energy is spiking up. That's what we want. But in that context, the gas with lower carbon footprints, that will be in slight incline. So what's going on in the US? So if we take a 7-kilometer well depth, as you can see, the western states are hotbeds. They offer excellent opportunity for generating thermal power because it can be all the way to 300 degrees C plus. As we go east and northeast, the prospect gets weaker for generating thermal power, but it'll be fine for serving different industries. So what do we mean by different prospects? So if we are producing pure geothermal fluids, which is done in about a dozen countries around the globe, the fluid temperature, outlet temperature is very high. So we can generate steam directly from their power. Whereas if we have lower temperature, and that is shown in this circle, if you so to speak. So we can generate the green cycle here. That's the power generation can still be done with the organic Rankine cycle. But for all others, different needs, as you can see, there's a literally long laundry list from agriculture industry to drinking water distillation to vegetable drying, on and on. We have a plethora of opportunities to use this hot water. So depending on where you are, this hot water can be generated. So how do we generate this hot water? So as the figure shows that we are in a given wellbore, we are introducing a relatively colder fluid of water. It can be other fluids such as CO2 or isobutane and pentane, etc. And then we produce it up the tubing, as we call it. So we are trying to take advantage of the thermal energy that is in play. So if we circulate, and generally speaking, we have two strategies. One is the continuous circulation. The other one is the stepwise circulation. So our preference is stepwise circulation. As you can see, we stepwise, we go up and then come down. This is the rate. And the main motivation for that is the near wellbore fluid temperature remains stable. It's within 1 degree C, because we don't want to keep circulating continuously to cool off the near wellbore system. And the same thing happens in this context. What happens to the bottom hole temperature? It cools down and then it comes up. And that's why we try to follow the strategy, and it can be optimized. I will now turn it over to my colleague, Dr. Sharma.
Thank you, Professor Kabir. Next slide. So first thing we wanted to do was to compare the stepwise fluid circulation approach with a continuous injection approach. So the plots that you see at the bottom are the plots between wellhead temperature and the injection time in days. So on the left, there is a comparison between stepwise injection of 3.2 meter cube per hour to 12.8 meter cube per hour. And we are comparing it with the continuous injection of 8 meter cube per hour. Here we used 8 meter cube per hour because if you go from 3.2 to 12.8, the average flow rate comes out to be 8 meter cube per hour. In this scenario, you see that there are some ups and downs. So you go lower than the continuous for some duration, and then you go higher than the continuous in some duration. The real change happens when we pair the stepwise injection. So on the plot on the right, we have two wells who are injecting 3.2 to 12.8. The another well is injecting 12.8 to 3.2. So one well is going low to high, and another well is going high to low. So in this scenario, we are always producing 16 meter cube per hour. So the comparison is done between continuous injection of 16 meter cube per hour. Here you can see the average. On average, we can get initially we can get 50 to 60 degrees C more improvement in temperature, which will translate to a higher power output also. Next slide, please. The next step was for us to understand that we know that stepwise circulation is giving us higher wellhead temperature and higher power output, but we wanted to understand what are the key variables which will affect this power output and which will affect this wellhead temperature. So in this slide, we are trying to show what are the key parameters. We set up a design of experiment to understand the key parameters. So here we are showing the results of the design of experiment. So here we can see that tubing ID, casing ID, circulation fluid temperature are the highest impact for outlet temperature, and then minimum circulation rate and maximum circulation rate are in the lower end. So only the construction parameter or the geometry of the well, you can control a lot of your outlet temperature. On the right, we saw a cumulative distillation plot of this design of experiment. Next slide, please. For power output generation, as you can see, the things move around. It's the same design of experiment, but instead of temperature, now we did it for power output. So here you can see that the casing ID is the highest, and then circulation fluid temperature increased to the second point. So the learning from this exercise we got is that circulation rates are always in the lower bounds for affecting the power output and temperature, but the well geometry is the controlling parameter in both cases for well temperature and power output. And then on the right, we see a cumulative distillation plot where you have a very smooth cumulative distillation plot. Next slide, please. So based on the design of experiment, we wanted to highlight some of the learning from the design of experiment. So here you see on the left, there is a plot between wellhead temperature versus time at 3 different injection temperature. So the major point that we took out of this is even if you are injecting at 25 degrees C or to 50 degrees C, by changing the well geometry and well geometry and well diameters, you can get a similar profile for even 25 and 50 degrees C. However, 75 degrees C is a higher step change, which can be achieved if you move around the well geometry again. Next. Similarly, on the right, we show that power has the same profile. We can achieve for both 25 and 50 degrees C injection temperature. By changing the well geometry, we are able to achieve similar power output profile, and 75 degrees is a higher step change. Next slide. We were encouraged by these results, and we wanted to understand what kind of energy uses distribution we can get from the continental US. So we analyzed the data that was provided by SMU. They had approximately 1 million wells in their database. So this database included well location, well depth, bottom hole temperature. So based on this database, what we did is we calculated geothermal gradient for each of the locations in the US, and we divided the lower 48 states between 4 categories. So one category is where geothermal gradient is greater than 0.11 degrees centigrade per meter. So this category is where you can produce indirect use, and you can produce electricity right away. So as Professor Kabir explained in the initial slide, the western state has more potential. So that shows here. Another category is the green one, where the geothermal gradient is between 0.11 to 0.05 degrees C per meter. These states can be used for both indirect and direct use. Indirect, you will need some specific design modification to achieve that higher temperature, and direct use, we can use abandoned wells also. And third category was when geothermal gradient is 0.02 to 0.05. In these categories where we can use direct use right away, and as I said, for the green case, for indirect use, you might have to do some more geometrical changes in your well design to achieve the same temperature. The last category was the blue, where you have, sorry, can we go back to the last slide? Last category was the blue one, where you have very low geothermal gradient, which less than 0.02, which can still give you reasonable temperature for a direct use. Yeah. Next slide. So based on that, we created temperature profile for all 3 definition cases, and we wanted to see what kind of uses we can see at the edge definition of each geothermal gradient profile. So as you can see, at 0.11, for a long amount of time, more than 300 days, you can still achieve temperatures between 110 to 90 degrees C, which are suitable for indirect use or electricity generation. As we go down to 0.05, you can achieve temperature. Initially, you will achieve temperature higher than 90 or 100, but in longer term, you can use it for you can use it for process industry, because process industry require a temperature range of 70 to 80, as Professor Kabir explained in the previous slide. And in the third case, where we are going to 0.02, this is a lower temperature profile, but the temperature still, the water can be still used for direct use for floor heating. Next slide. So in the end, the major concern with the geothermal energy processes is the cost. And the biggest contributor is the well drilling and completion cost. So EIA provides inventory of duct wells since 2013. So the duct wells are defined as the well which are drilled but uncompleted. So as you can see in the plot, since 2013, there has been a slow increase in the number of duct wells. So these wells, in our opinion, provides a perfect opportunity, because your drilling cost is already taken care of, and you have opportunity to go and complete the well based on the design specification, which can be picked based on the use case. So if you want to use direct energy or indirect energy, you can go to the duct wells and utilize them. Duct well goes ups and down with the oil price, but however, there is a base of 4,000 duct wells which is maintained. So there is still a lot of potential that we can utilize there. In addition to that, for direct uses for geothermal energy, there are 3.2 million abandoned wells in the United States that can be utilized right away for direct energy uses. So from now, I'll give it back to Professor Kabir.
Okay, let us summarize the key takeaways. We see that we give you a hint of that. The cyclical fluid strategy is a better one than a continuous fluid in circulation. We have technical papers to that effect. And then both the casing ID and inlet fluid temperature have significant impact on power generation. So that's why our preference is to use the design wells as opposed to existing wells. So existing wells would be good for direct use in different industries. And some of the parameters are of item of interest. Larger casing ID will generate more power in design wells. And of course, geothermal gradient is very important, as Dr. Sharma just pointed out. So what we found that as far as the regional prospects are concerned, so we have at least 30 states that we can use for direct usage in the US, and about 5 states for geothermal, direct geothermal energy, meaning generating power. Thank you for your attention. With that, we conclude our presentation.